Artificial intelligence has an energy problem that almost nobody in the industry wants to talk about honestly. The four largest tech companies spent an estimated $650 billion on AI infrastructure in 2025 and 2026 combined. A single hyperscale AI training cluster draws up to 100 megawatts of power, enough to supply a small city. According to the IEA, global data center electricity consumption is projected to hit 1,100 terawatt hours in 2026, equivalent to Japan's entire national electricity use. And the grid cannot keep up. Utility companies across the U.S. are reporting that interconnection timelines, the process of connecting a new data center to the power grid, are already falling behind the pace of construction. This is not a future problem. It is a right now problem, and it is the reason a paper published by researchers at Tufts University in February 2026 is one of the most important things to come out of artificial intelligence this year, even though most people have not heard of it. The research introduces something called neuro-symbolic artificial intelligence, and the results are striking enough that they are worth slowing down on. Current AI systems, the kind that power chatbots, image generators, and robotic systems, learn through pattern recognition. They process enormous volumes of data and statistically learn what outputs tend to follow what inputs. This works, but it is computationally expensive because the system has no underlying understanding of why things work. It is brute force learning at scale, which is why it requires so much power. Neuro-symbolic AI takes a different approach. It combines neural networks with something called symbolic reasoning, which is the ability to apply explicit rules and logical structure to a problem rather than relying purely on statistical pattern matching. In plain terms, it teaches AI to break problems into steps and categories the way a human does when thinking through a task deliberately. The results from the Tufts team, led by Professor Matthias Scheutz, are not incremental. Their neuro-symbolic system achieved a 95% success rate on a structured robotic manipulation task. The best performing conventional system managed 34%. Not 34% below neuro-symbolic, 34% total. The conventional model was failing more than 2/3 of the time on the same task, where the new approach was nearly perfect. And the energy numbers are where it gets genuinely striking. The neuro-symbolic system used just 1% of the training energy required by the conventional model. During task execution, it used 5% of the power. That is where the 100 times figure comes from, and it is not a cherry-picked edge case. It held across structured long horizon tasks, the kind that are directly relevant to robotics and real-world applications. The paper will be formally presented at the International Conference on Robotics and Automation in Vienna in June 2026. This research does not exist in isolation. It is part of a broader shift happening across artificial intelligence right now, a move from raw scale to architectural efficiency. Google published the TurboQuant algorithm at ICLR 2026, which compresses AI memory requirements through a technique called 3-bit KV cache compression with near zero accuracy loss. The problem it solves is different from Tufts, but the direction is identical, making AI systems dramatically more resource efficient without sacrificing performance. These are not marginal improvements. They represent a fundamental rethinking of how artificial intelligence should be built. The practical implications of this shift are real and concrete. The cost of running AI is one of the primary barriers to adoption, particularly for smaller businesses and organizations that do not have enterprise infrastructure budgets. When a technology requires data centers consuming city-scale electricity, access concentrates at the top of the market. When that same capability can be delivered at a fraction of the energy costs, that concentration breaks down. The Tufts architecture points toward a future where AI tasks that currently require expensive cloud compute could run on much lighter hardware closer to where the work actually happens. That means faster response times, lower costs, and access for organizations that currently cannot afford to compete. Every order of magnitude drop in the cost of running artificial intelligence has historically opened up new categories of use that were previously economically impossible. A 100 times reduction is not one order of magnitude. It is two. There are important caveats worth naming here. The Tufts research was demonstrated on structured robotic manipulation tasks, specifically the Tower of Hanoi problem and similar benchmarks. Neuro-symbolic approaches have historically struggled with the kind of open-ended, unstructured tasks where large language models currently excel. The architecture is not a universal replacement for current AI systems. It is a powerful complement in domains where logic and structured reasoning matter most, which includes robotics, manufacturing, and any application involving sequential decision-making with defined rules. But the broader signal is clear. The assumption that artificial intelligence must consume exponentially more resources to become exponentially more capable is being directly challenged, not just by one team, but by multiple research groups across multiple institutions simultaneously. The AI industry built the last 5 years on a philosophy of scale. More data, more compute, more power, more capability. That philosophy is not wrong, but it is incomplete. And the research published in 2026 is starting to demonstrate that a different approach, one built on efficiency and reasoning rather than brute force, can outperform the current paradigm on specific tasks while consuming a fraction of the resources. That is a significant finding. And the window to understand it before it reshapes the market is open right now. If this changed how you are thinking about where artificial intelligence is actually headed, subscribe and leave a comment. Do you think efficiency breakthroughs like this one will democratize AI, or will the big players just use the savings to scale even further? I want to know where you stand.